By the end of today's lecture, you should have more than enough information in order to complete this particular problem set. Question 1 requires use of the graphing utility like Excel. Evan will tell you more about that in his TA sessions. So if you have any questions on the actual mechanics of using Excel to plot data, feel free. Okay? All right. So what I want to do today is pick up where we left off, and I want to finish up the solo growth model. We're going to bring in the solo growth model. We're going to finish the question that we posed at the end of class on Tuesday. Then issue number 2, we're going to talk about solo growth and technological change, explain the solo residual. Then we will talk about the strengths and weaknesses of the solo framework, informed as ever by Dr. Easterly. Then we'll take a turn and talk about endogenous growth theory. Of course, solo growth model, the core conclusion is that technological growth is an exogenous variable. So endogenous growth tries to explain for economic growth and technological change inside of the model. Yeah. And then we'll talk about two-sector models, and then we'll end it with some Marxist responses to the neoclassical model. Okay, so depending on people's persuasion, we'll end with that. Okay? We'll attempt to take a break after issue number 3. Right? So, at the end of lecture on Tuesday, I posed a question to you all. I said, given a per capita production function, y equals 10 times k to the 1/2, a savings rate equal to 20%, a population growth rate equal to 2%, and a depreciation rate equal to 3%, I asked, what are steady state values of k and y? So based on this information, what are the steady state levels of capital stock per capita, k star, and income per capita, y star, in the solo growth model? Now, before I solve this algebraically, and I'm sure some of you attempted to do this last night or on Tuesday, I want to remind you of how the solo model works graphically, because this is critical for your problem set, but also just broadly critical for your understanding of neoclassical growth theories. So, what's the most prominent characteristic about the solo growth model's production function? Diminishing returns. That quality gives the solo model production function that shape. Okay? Each subsequent increase in capital stock per capita in equal increments yields ever-falling amounts of marginal output per capita. Okay? That's the first major aspect of this graph. Furthermore, we have some savings rate. And because we're dealing with a closed economy, we know what about savings and investment? They're equal to one another in aggregate terms and per capita terms. Savings and investment equal one another in per capita terms and aggregate terms. So we can plot investment per capita or savings per capita like so, S times Y. So for any given capital stock per capita, what is my consumption per capita? How would I figure that out graphically? B, for any given capital stock per capita, what's my consumption per capita? Recalling that in the solo growth model, it's a closed economy, so there's no net exports, and there's no government sector. So all income is broken between investment and consumption. Where's my consumption graph? Yep. The delta between these two. Okay, so if I were to have a k right there, graphically we just plot this k into our production function and get some y. We have y right there. Okay. And we also know that at this particular capital stock, investment is here. So the difference between investment and income must be consumption. Very good.
So if you add the bottom part and the top part, That's total per capita income.
Exactly.
Divided up into two uses that were specified on the graph.
Yep. Good question. Secondly, if the savings rate were to increase, what shift would that precipitate on the graph? Just an exogenous increase in the savings rate. Yep.
Consumption was shrink.
Okay, that's good, but how would we know that graphically? You're right.
The line would shift up.
Which line?
The savings line.
Yep, exactly. Savings per capita line would increase if the savings rate went up, with S2 being greater than S. Thank you. Appreciate it. So, as the savings rate increases, you know, one, that consumption will go down and investment will go up. Investment goes up and consumption falls by the same amount for any given capital stock per capita. Make sense?
Say that again.
Sure. So for any given capital stock per capita, okay, if we raise the savings rate, that raises investment. And because per capita income is unchanged, consumption must fall. So this is the production side of the economy, okay? Now, further recall that we're missing one element of the solo growth model. Remember the law of motion of capital, delta K, which is equal to S times Y minus depreciation plus population growth rate times the pre-existing capital stock. In any given period, the amount we add to the capital stock is S times Y. I repeat, in any given period, we usually measure those periods in years. In any given year, the amount we add to the capital stock is equal to S times Y. And that makes sense, because savings times income is investment. And investment leads to deepening of the capital stock per capita. Okay? So you could think of this term here, I'll call it term A, as being a net increase to the capital stock per capita. Okay? I'm sorry?
There is still the glare that I think it comes from the, I don't know where it comes from.
Yeah, I'll lower the blinds a little bit. Better? Maybe you could probably move if it's.
Yeah.
Oh, the fluorescent light? Yeah, this is one of those optimization problems that I'm not fit to solve. Sorry. Okay, so remembering the law of motion of capital, right? This curve A here corresponds to a given savings line here, yeah? This income corresponds to this income. Right? That income function corresponds to this production function. Okay? See that? You have a question?
Sorry, can you recap?
Yeah, sure. So this income right here
Yeah.
is determined by the production function,
Right.
which we have graphed right here. So in other words, we can plug in our function into this y. It'll be a little clearer when we actually solve the question. Okay? Now, this is just the production side. We also have the depreciation and population growth rates we have to deal with. Think about this intuitively. As the depreciation rate rises, our capital stock per capita must shrink. If our capital stock becomes less durable, our capital stock per capita will have to fall. Moreover, as the population growth rate increases, our pre-existing capital stock has to be spread across an ever wider pool of labor, thus decreasing the capital stock per capita. That's why this is why we subtract this term from investment. Does that make sense on a per capita basis? Okay. So I'm going to draw a fresh graph, use it to talk about the Solo model graphically, and then we will solve the question.
What would you call this first one, if there is a name to it?
The first graph?
Yeah, no, this one.
The one I just erased? That's the basic, that's just the basic Solo growth model.
Okay.
Mhm.
Just to know.
What, I'm sorry?
Just to know. for
Yeah,
future
to signpost it,
reference.
sure. No worries. Now, this is the complete Solo growth model, okay? Absent technological change. We have our savings line, just like we had before. We have our income line, just like we had before. And now we graph our depreciation line. It is a constant slope, because these are both fractions, or percentages, so this is the equivalent of just a basic linear function. Okay? That's why there's no curvature to the line. Make sense? There's no exponent, it's just k to the 1.
I'm sorry, what was fractions?
These two rates right here.
Okay.
So for instance, let's just say, forget the Solo growth model for a second. Let's say I gave you an equation, y equals 1/2 x, right? That would just be a straight line from the origin with slope 1/2. That's the exact same logic of why this is a straight line here. Okay? Now, what's true about the steady state level of income per capita in the Solo growth model without technological progress? What two things equal one another in the steady state? Or what is the nature of growth in the steady state? Yeah, Sam?
Savings and depreciation would equal each other and there's no change in K.
Very good. So the first is that delta K equals 0 in the steady state. Delta K equals 0 in the steady state. So we can solve this algebraically by setting this equation equal to 0. And thus, we can see clearly that S times Y equals depreciation plus population growth rate in the steady state. Right? Because this whole line equals 0, we just simply add over the depreciation line to both sides, and they equal each other. Everybody see this? Like, look, literally, can you see that? Okay.
Why do you want to do that again? What are you trying to do?
I'm sorry?
What are you trying to do by doing that?
By doing what?
You're setting at 0 and
Yeah,
you're
so I'm stating that in the steady state, capital stock per capita doesn't change.
Right.
And then based on that insight, I'm using the algebraic representation of the change in capital stock to come up with some steady state condition, which is this. In the steady state, investment equals depreciation. The amount you add to the capital stock is perfectly offset by the amount of your capital stock that depreciates away. Those two things have to equal each other. Okay? So graphically then, where's that point? Where do these two curves equal each other?
The cross.
Exactly. I had an economics professor who used to say that everything in economics takes place either at an intersection or a tangency. So this is an intersection. Okay? I'm going to call it K star to indicate that it's my steady state level of capital stock per capita. Now, why is that the steady state? Why is it that all other capital stocks per capita in this model trend towards it? Who could explain that intuition? Let's say, hypothetically, our capital stock per capita were here at K1. What's true at K1? Yep.
The reason they changed to that is because that's where you get the maximum, trying to think of the word, but that, it doesn't make sense to invest anymore, but you're also, there's still, it hasn't fully depreciated.
At the steady state?
Yeah, that's where the two of them equal. And
Perfectly
so you
offsetting
can-
one another.
so you
That's
can
correct.
Maximize your capital.
Sure, because anything greater than that, it would necessarily go back down, right? But why is it that at K1, why do we expect the capital stock to increase until it hits K star? This intuition is critical for the solar growth model, so I'm spending some time on it. Yep,
So don't you have unused savings and it would be used up slowly until it reaches a steady
that's
state?
exactly it, okay? The best way to think about this, try to draw this as fluid as possible. At K1, we have some S times Y and some depreciation. Okay. Term A is bigger than term B, right? Investment is greater than depreciation. And anytime investment's greater than depreciation, what's the sign on the capital stock per capita change? Positive. Delta K is greater than 0. Therefore, any capital stock less than our steady state will necessarily lead to the steady state because savings is greater than savings and therefore investment is greater than depreciation, thus leading to an increase in the capital stock until you hit the steady state. I'll get you in a second, Jürgen. Does that make sense to people? Right? Just look to the graph. Anytime there's a difference between them, A is greater than B, savings is greater than depreciation, we're going to be moving in this direction until we hit that equilibrium. Yeah, Jürgen.
Could you have the reverse?
Absolutely.
Could
So
you
why don't
have
you
a
walk me
higher
through
depreciation than the savings rate?
Why don't you walk me through that? So let's say hypothetically we are here, K2. Is that sustainable?
Not over long term, no.
Not in the long term. Why? Because when we have K2 level of capital stock per capita, what's the relationship between investment and depreciation?
B is greater than A.
Exactly. Depreciation is greater than investment. So we know that delta K has to be negative, less than 0. Therefore, for any capital stock greater than our steady state level of capital stock per capita, we necessarily will trend back to the steady state by a fall in capital stock per capita.
And my question was, could you have a situation where you don't have a steady state, where your depreciation starts to be higher than the investment?
Oh, I see
So
what you're
the
saying.
moment
I
you
see what
put
you're
money
saying.
in, you already lost it.
Yeah, if you have an incredibly low savings rate, yeah, then your steady state would just be 0, right? If you have a really high population growth rate and depreciation rate and a really low savings rate, that intersection is going to be as close to 0 as you can make it. So yeah. But then too, you'd have a steady state. They'd still intersect just at the origin. Okay? Yeah, Win.
Maybe this is getting away from the model a bit too much, but I'm curious, in a situation where you have like, I guess I'm trying to imagine kind of like what the steady state would be. Like for example, in the US, lots of investors don't want to invest in the US, they're looking to go somewhere else because there aren't lots of returns. Like, is that the same kind of like investment? Like when you're on the far right, is it, you know, the idea that there are lots and lots of investment opportunities and so savings will increase because you can find good returns, or I mean.
Yeah. So the way we kind of turn this into policy, we'll get to in a bit. But just to explain, you raise a good point about the role of international capital here, because that's the real where the rubber hits the road in terms of how we make lending decisions at the international financial institutions. But think about it this way: the return on capital with the low capital stock per capita is much higher, right? Just taking the MPK than in a mature economy. And so the theory would postulate that capital should flow from rich countries to poor countries, which would then allow them to catch up and achieve their steady state. And yet we find, the Lucas critique that capital doesn't really flow from rich to poor. It actually flows from rich to rich and often poor to rich. So there's many different incantations in that. Okay, good question. Does the algebra behind the law of motion of capital make sense in the context of how the steady state's achieved in the graph? More or less? Yeah.
Are you supposed to plug numbers into that?
I'm so happy you asked that. So,
And actually arrive at an answer, and if so, where does the answer appear on the graph?
that's a fine question. So why don't we do the question I left you with on Tuesday? So recall, this is all given to you, okay? Just like in your problem set. That's why we're doing this. So, we give you a savings rate, we give you a population growth rate, we give you a depreciation rate. We must solve for K star and Y star, okay? So, at the steady state, we know that delta K has to equal 0. Therefore, investment has to equal depreciation. So, let's plug it in. What's our savings rate? It is 20%. So we'll say 0.2. What's our income? What do we plug in for there?
10 times little k to 1.
Exactly. 10 times K to the 1/2. Because that's our per capita production function. Okay? S times 10 times K to the 1/2. Depreciation, 3% plus population growth, 2% equals 5%. So we can say this is 0.05 K. All we're doing is taking what was given to us, the per capita production function, the savings rate, population growth rate, and depreciation growth rate, and plugging it in to our law of motion of capital steady state condition right here. Okay? So from here, math happens, and we are left with 2 divided by 0.05, quantity equals K to the 1/2. So step 1, step 2, step 3. It's equal to 40 equals K to the 1/2. Or 1600 equals K star. Circle all final answers.
You said number 3 is 40?
Yep, 40 equals K to the 1/2. Right, 2 divided by 1 over 20, denominator, denominator, numerator, 2 times 20. That wasn't so hard, right? Just plug it in. Just make sure you write these steps down, and then what you can do is just make up your own values to practice. Okay? But make sure you get the steps down conceptually, or at least in your notes very clearly. Okay? So, I have this K star now. Where is this K star on my graph? Let's just say these equal all the right values. Exactly. That's this right here. Okay? 1600 is this. So what's my steady state level of income per capita? So how would I figure it out? Sam?
Didn't you plug it back into the production function?
Absolutely. So we have our production function right here. We simply take Y star is equal to 10 times 1600 square root, which is equal to 400.
So, Neil, if you asked us, for example, how to find consumption,
Mm-hmm.
would we just take the income level and then subtract out the investment?
That's exactly
and
it.
then just, okay.
And on that point, let's figure out what's investment and consumption. But before we get there, does everybody see how we solve for the steady state level of capital stock per capita and where we got income per capita? Yep.
In the last section, you had that circled y equals 10 times k to the 1/2 up there.
Here? Yep.
Yes. Is that what you just did to get the
Exactly.
400?
I took this and just plugged it in there.
That's, and then you came up with 400 equals y star, right?
Yeah.
From that?
Mm-hmm. Square root of 1600 is 40 times 10 is 400. Alright. So, and that of course corresponds to this value right here. Say we had 400 right there and 1600 right there. Alright? Now, what's my investment? How would I figure that out? Wait.
I just had a quick question.
Yeah.
Could we like double check this by plugging that value in that
To here?
SY?
Yes. That's a good way. Yeah, just plug in everything and make sure the left side equals the right side. So how do we solve for investment? Yep,
It's S times Y.
exactly.
Yeah.
So if y is 400, s is 20%, 20% of 400 is? Anybody? 80. And if investment plus consumption equals income per capita in the solo growth model, and investment was 80, and aggregate income was 400, what is my consumption per capita? 320. Where it is graphically, you can see here. Now obviously the scales don't match up, but this would be 80, and then this difference would be 320, which would be equal to consumption. This quantity would be equal to investment. Everybody see that? Any questions? If it makes you feel better, this is probably the mathiest this class will get.
That does make us
That
feel
does
better.
make
Can you
Yeah.
please go over the 80 again? 20% of 400, right?
Yep.
And
So 10% would be 40, and then
And then you just subtract it to get the assumption.
exactly. We take, because we already know 400s are income. Now we know 80s are investment, so the difference has to be consumption.
I'm sorry. Can I just get one more detail?
Sure.
Investment is the formula for investment is S multiply Y, right?
Exactly.
Okay.
Now, this is how you solve a quantitative question using the solo growth model, okay? This mirrors very heavily your problem set, okay? So, yeah. Once you learn how to do this, the problem set will really solidify, okay? Then when you get the question on the test, you guys will kill it. Okay? Maybe. Might not be on the test. Okay, so I want to cover a couple more things with solo, and then we will move on. Everybody got this right? Right. Okay.
Can you draw the depreciation line at
Harvard? In different color you want, or just
no, it doesn't show up at all.
so you can see it? Okay.
Yeah.
A fair request. Okay. Looks like a third grader just drew that. So, two things. In the steady state, absent technological progress, what's my change in capital stock per capita? 0. And therefore, what's my change in income per capita? 0 as well. Okay? In the steady state, delta K equals 0, therefore delta Y is also equal to 0. This is a main insight from Solow. He claimed that once we hit the steady state, growth would have to stop, absent technological progress. So there's two shifts I want to cover here, and I want to analyze their impact on aggregate income. The first shift is an increase in savings, okay? If savings were to increase, my investment line would increase. S1 less than S2. And we would have a new steady state, K star 2, K star 1. And per capita income would thus be higher. Increase in savings would shift up this line. You guys see that? Which would lead to a higher steady state, which would in turn yield more income per capita. So the upshot here is that an increase in savings leads to a greater amount of investment per worker. As a result, this is no longer our steady state because investment's greater than depreciation here. You guys see that? This can no longer be our steady state because on the new investment curve, that's actually greater than our depreciation line. Thus, capital stock per capita will gradually grow until we hit our new equilibrium. As savings increases, investment goes up, which leads to a permanently higher stock of capital per worker and a permanently higher income per worker level.
Why does income go up?
Because the capital stock per capita steady state is also higher. And it's a function of it, income's a function of it. Now, Solo's keen insight was as follows based on this. Those economies that save more will have a higher standard of living than those that save less. Because those countries that save more will have higher per capita capital stocks in the steady state. When?
Could you explain the difference? I'm just getting a little confused between shifting up the savings line and moving along it, because just earlier we were talking about having like excess savings and how that would come back down.
Movement along the savings line is really determined by whatever your capital stock per capita is. Movement of the savings line is determined by your savings rate. Okay? Yep. Movement along the capital stock, movement along the savings line is a function of the capital stock per capita. Movement of the savings line depends on changes in the savings rate. Now, once we increase our savings rate, in the long run, is our rate of economic growth any higher? Once we increase our savings rate and we get to K star 2, is our rate of growth any higher? No, because our capital stock hits a new steady state, and that's that. So an increase in savings can only lead to a temporary increase in the growth rate of income per capita. Because once we hit the steady state, growth stops.
I have a question.
Yeah.
The readings and the discussion here refers to the long run, and the long run this, et cetera. What's the difference between the long run and the short run?
When we hit the steady state.
Is it,
Oh, when we hit the steady state?
where is the long run on that graph?
The long run would be when our capital stock per capita equals that. Let's say we're humming along here, right, at K star 1.
Right.
We exogenously increase the savings rate, which, boom, shifts up the savings line.
Right,
It's not the long run at that point because our capital stock is still here.
right.
The slow movement to that capital stock, the new one, once we hit the new one, that's the long run because it's its natural equilibrium.
And what does the long run mean? That's the way it's gonna be over
Exactly.
permanently?
It's in equilibrium. It's not going to change.
Right, is there such, can you identify the short run on that graph?
The short run would be the process of moving from the original equilibrium to the new one.
Okay.
Okay. Now that's the shift in savings. Another shift I want to talk about is the shift in population growth. I'm not going to draw in the income line, okay? I'm just doing savings and investment and savings depreciation, or else I'll get too cluttered. Okay? Imagine an income line just kind of, neatly above, just like that. Okay? So we have our savings times income. We have our old population growth rate N1 plus the depreciation rate times K, which gives us K1. Okay? Now, for whatever reason, the population growth rate of this country increases. Okay? The increase in the population growth rate, we'll say N2 greater than N1. What will that do to my graph? Jürgen? Shift
the
it?
straight line.
Yeah. So recall, just be careful. Instead of saying shift, you might want to say pivot. Just a little clearer. Because it's still anchored at the origin. Something like that would occur. Depreciation plus population growth rate N2 times K. Okay. And what would happen to my steady state level of capital stock per capita in the long run?
Fall.
It would fall. It would go to the new steady state right here, K2. And we would have ever falling levels of capital stock per capita until we hit K2. The greater the population growth rate, the more workers an economy has. And thus, the more workers an economy has, the more the capital stock per capita will be spread out. Okay? Spread out among a greater number of workers, thus decreasing our capital stock per capita and lowering our per capita income.
We're using the terms labor force, workforce, and population synonymously.
Synonymously, yeah. And just the only difference is, be careful when I say there's aggregate population, okay? And then there's the rate of change of population, or population growth rate, separate concepts, okay? There are two kind of conclusions that Solow arrives at. The first is, two countries with the same level of income, no, ignore that. Okay, what I want to talk about now is applying these two shifts to the realm of economic policy making. And I want to put you in the shoes of Deng Xiaoping, and I want you to tell me how to increase China's income using the Solow growth model.
Well, decrease the rate of population growth, obviously.
Okay, that's a good one. That's definitely a good place to start.
Would you increase savings?
That's also another good one. Wow, you guys beat me to the punch. To see this graphically, okay, so Deng Xiaoping inherits a destroyed economy because of Mao Zedong, and as a result, he faces a China that looks something like this, okay? Its population growth rate is N1. It's a fairly high population growth rate. You don't get to 1 billion people without having some semblance of rapidly increasing population. And also, it has some savings rate S1, okay, which is very low, namely because of collectivization and all these other horrible things Mao did, okay? So as a result, our per capita capital stock is at K1 star, which gives us a per capita income of Y star, which is very low, which is actually tied with India's per capita income in 1980. Now, you're Deng Xiaoping. You say, okay, I can control all the variables in the Solow growth model except for total factor productivity growth and my actual production function. So what two changes are you going to institute in order to increase the steady state level of capital stock per capita in your economy? As you said, you will decrease the rate of population growth. That's the first thing, right? So that's the equivalent maybe of a one-child policy. So once you decrease the rate of population growth, our depreciation line looks something like that. depreciation plus N2. Okay.
Is N an absolute number, or is it I'm trying to remember, is it just the absolute population?
No, it's the
Okay.
rate of change
It's
of the
rate of change,
population.
okay.
Okay? Think of it like a birth rate is something
Okay.
that's loosely corresponds to. Good question. It's a good question because that nuance is important on your problem set. Yeah. Now you're all wondering, what part of what question is that important? You'll remember, don't worry. Okay. And what else did he do? Well, that's one thing that would increase the capital stock per capita. But he also started to amass a process of export-led growth, which led to large savings, which in turn allowed their savings rate to increase, S2 times Y, further raising China's steady state level of capital stock per capita. China's growth over the last 40 years can largely be understood in the solo growth framework, I would posit. Yeah, there's a lot of other stuff at play. You need an authoritarian government that allows you to do these things. But fundamentally, I think senior Chinese leadership understood the fact that population growth can be a huge drain on per capita income, and that rising savings can be a huge boon to investment and in turn aggregate income and per capita income. Yes?
Can you decrease the depreciation? That means write everything off or destroy everything?
Yeah, you can change the depreciation growth rate maybe by having more sustainable investments. That's an example of it. Yeah, it's not really part of the Chinese playbook. Yeah?
Yeah, if he could have done either or,
Yes.
but he wouldn't get the maximum growth.
Yeah, doing one in and of itself would help, but doing both in concert, as you can see, right? If you, for instance, if you were just to change population growth rate, it increased the steady state level of capital stock per capita here. Okay, if you were just to increase the savings rate, it would only increase it to here. Doing both in concert, see the difference?
It's like a multiplier effect, right?
Mm-hmm. Yep. A lower rate of population growth allows you to make better use of your investment. If you save more too, that's going to induce growth. Right? And by the way, this process of going from here to here, right? That's where you get 8% growth year after year. Right? If you believe the Chinese statistics, which some of us don't. Leave that to you to decide. Yeah?
Is it just an accident in the graph that you projected China to hit the point of diminishing return?
Maybe they're somewhere around here. Who knows? Unclear. Actually, I have an article to that effect that I will pass out at the end of class on China specifically. Okay? Cool. So that's the solo growth model. This is all, of course, absent technological change. Okay? But based on this, you should be able to answer the entire solo question on your problem set for sure. And yeah. Any questions on solo model absent technological change? Yeah.
You referred to China's model of export-led growth, but we're talking about a solo model in which it's a
closed economy. Yeah, it's that's just kind of one of the model doesn't apply necessarily completely to real life. Like whatever the source of increased savings were, right? Just assume it increased exogenously, and that's why. Ultimately, it came from the fact that they're making large export revenues, which then went to government coffers, allowed them to increase public savings, increase incomes in the countryside and also in urban areas, which allowed them to have higher private savings. That's just the trigger for why S went up, though. So it's not incorporated in the model. See the difference? Just imagine if it were just an exogenous increase in S.
So in terms of the problem set and perhaps the midterm, necessarily worried about that.
No, what you would need to say, for instance, if you were given this, right, and you were here, and you wanted to increase your steady state level per capita income, and you said, what are two ways you could do it? You could say increase savings and also decrease the rate of population growth. That's more than sufficient. Okay? And just explain why. Good. Yep.
Isn't that always going to be true for any country? Or if you use the solo model?
Yeah. Yeah, it's not unique to China. I just like that example. All right. So what we know so far, let's do a little recap on rates of economic growth. We know that in the steady state, in the solo model, the rate of change of labor is equal to N. The rate of change of capital stock per capita is equal to, in the steady state, is equal to 0. And therefore, the rate of change of per capita income is also equal to 0. What's the rate of change of aggregate income? Not per capita, but just big Y, not little y.
Change of population.
It's the rate of population growth.
So it's equal to N?
The rate of aggregate income, right? So delta big Y over Y is equal to N
Yeah.
in the Solow model. Okay? Think about it. If our per capita, the rationale being, if our per capita income has to stay fixed and labor is growing at rate N, then our income has to grow at rate N in order to maintain per capita income. Okay? Alright. Now, the main problem so far in the Solow growth model is that once the economy reaches the steady state, economic growth simply matches population growth. Aggregate income growth equals N. Moreover, there's no growth in per capita income, and yet countries still grow. So Solow tried to answer this conundrum by introducing the concept of technological change. Solow observed that in the United States, UK, France, Germany, we have very long periods of sustained growth in per capita income, which are made possible by technological progress that allowed output per worker to grow. Now, in order to see how we modify the Solow growth model for technological change, we must redo the model accordingly. Now, what we're going to claim here is that we have some level production function. Okay? And it's still a function of capital in labor. But we modify it slightly by introducing a term known as technological progress, or T. This T could be considered some labor-augmenting technological change. Having a greater T is the equivalent of having a greater L. And yet with L fixed, as T goes up, so too does Y. The way to think about this in terms of efficiency is as follows. As T goes up, the efficiency and productivity of labor increases, since the same amount of labor can now produce more output. The combined term T times L then we refer to as the effective amount of labor. Technological change allows output and income per worker to increase, even in the steady state. I repeat, technological change allows output and income per worker to increase, even in the steady state. To understand why, let's redo the model. So we can claim, just as we had some income per capita, little y, equals big Y over L, so too can we have some income per effective worker, YE, which is equal to big Y over T times L. Furthermore, we can claim that we have some amount of capital per effective worker, which is equal to big K over T times L. Does this part make sense to everybody? Any questions on where we got this?
What do you mean by effective worker as opposed to non-effective worker?
The difference is this increase in T will increase L is if, let's just make up numbers, right? Let's say we have our technological progress is 2, and we have 100 people working in the economy, then the income will be as high as if we had 200 workers, even though we only have 100 workers. So it's the equivalent of, it's effective workers. It's because of technological change, our labor force is growing, but not really. Our labor force is still fixed.
Technologically equipped worker.
Yes. So we can also have a law of motion of capital. The rate of change of capital per effective worker equals the following. Again, we have savings times income per effective worker. But now, I posit that the rate of change of technological progress is equal to some theta. The rate of change of technological progress is equal to some rate. We're just going to call it theta. Thus, our depreciation of capital stock per effective worker also increases at rate theta. This capital stock per this theta is the equivalent of population growth rate of effective workers. Okay? This new term, I'll call it term B, as I often do, is larger than simply n plus depreciation times k, indicating that more capital is needed to keep capital per effective worker constant. Because this term is greater than this term B greater than this one, we know that more capital is needed to keep capital per effective worker constant. It's the equivalent, to increase in technological change is the equivalent of an increase in the population growth rate.
Quick question.
Yeah, Jürgen first.
Isn't that supposed to be a positive theta? The
Yes.
technology advancement is what we're actually having a negative here.
We'll get to that. Just let me finish it up. Yeah.
Yeah, I was just saying, intuitively you think technology would actually increase efficiency,
Yep.
and therefore.
So there's now two kind of solo models you need to be aware of. Okay? We have savings times income per effective worker. We have our income per effective worker. We have our capital stock per effective worker. We also have our depreciation plus population growth rate plus our rate of technological progress times effective worker. This gives us our capital stock per effective worker in the steady state. Now, in the steady state, what's the rate of change of our capital stock per effective worker? It's a steady state, so it must be 0. Yet, effective workers aren't real workers. The actual amount of labor supply is still growing at rate n, not rate n plus theta. So the way to think about technological progress is an exogenous increase in our per capita income function in the old solo growth model. Is the rate of technological growth increases, you think of that as an increase in the total factor productivity of our factors of production. They're more efficient. We can produce more with the same exact amount of inputs. That's equivalent to an increase in our income per capital line. The way to envision this, if we had some K over L here, we can do more with our given amount of inputs. That's exactly what's indicated by this shift. Another way to think about this is to recall our various growth rates. In the steady state, we know that delta capital per effective worker equals 0. We also know that the change in income per effective worker also equals 0. We also know that change in labor force equals N, and the rate of change of capital per effective worker, or excuse me, technological progress per effective worker is equal to N plus theta. Right? It's the equivalent of having more and more workers as technological progress goes up. Therefore, we know that the change in income, this is aggregate income, not per capita income, is equal to N plus theta. And here's the kicker. Our rate of per capita income growth is now just theta. That's why technological progress is so important to Solow. He claims that that's the only source of sustainable increases in per capita income. Full stop. That's the biggest insight of Solow.
Could you repeat the connection between the two graphs again?
These two, yeah, it's basically, you can think of it this way. An increase in theta is the equivalent of less capital per effective worker, right? Because it'll shift the entire depreciation line left. And yet, your actual number of workers remains fixed, right? So that change, the increase in the number of effective workers, actually is the equivalent of an increase in our total production function. Because we can make more with any given combination of inputs than we could before the technological progress change. That's the connection. If this part's a little fuzzy, it's okay. What I really want you to be aware of, though, is this insight. The whole notion that the only way to have sustainable per capita income growth in the Solow growth model is technological change. And be able to show on the bottom graph why an increase in technological change will actually increase our per capita income line. Yeah, thank you.
Say this one more time.
Mm-hmm.
Technology is the only source of a sustainable increase in what?
In per capita income. Recall. Oh yeah.
I'm
Question.
sorry, can you explain again, please?